Priyanka by Cloud Tutors, a program for grade 10 students to help prepare for their board examinations. Today we'll be looking at the light chapter, which has a total weightage of around 7 to 10 marks. Let's look at a particular topic from light chapter, that is reflection of light. Before we get into actual session of reflection, let's look at what is the weightage of this chapter, what kind of questions do we get, and a few points to remember during the preparation of your board examinations. Let's get started. So, as I already mentioned, light as a whole chapter weighs around 7 to 10 marks. When I say weighs around, it just means 7 to 10 marks of what the questions may be appearing from the entire chapter of light, which includes reflection of light by plane mirrors, spherical surfaces, refraction of light, all of these topics. In this topic, that is reflection of light in particular, has a weightage of around 3 to 4 marks. So when it comes to the kind of questions that may appear from this topic, it is basically numericals are always from the topic of spherical mirrors, wherein you need to locate the images, where is it formed due to a convex mirror or a concave mirror, so on and so forth. 1 or 2 mark questions are always based on the definitions or either on the magnification of the mirror, or you may be asked to calculate the focal length using the radius of curvature, and so on. So the first important thing to remember and to work upon are the ray diagrams when it comes to the light chapter, especially in a reflection and refraction chapter involving lenses and the spherical mirrors. So please remember that you need to concentrate on the arrow marks which show you the direction of the rays that you intend to show. If you have put the arrow marks as in an opposite direction or in a wrong direction, you will tend to lose mark over there. As we already discussed, most of the long answer questions are based on the numericals or the spherical mirror problems. As I've told you already, 1 or 2 mark questions, that is the short answer questions, are mostly definition based or understanding based as such. So with this understanding and with these simple tips to remember, let's look at what are the topics that come under reflection of light chapter. So whenever you are preparing for an examination, it is always overwhelming. It is completely understandable, right? So what can we do in order to reduce our burden, or not to be overwhelmed with the amount of things to be studied? Simple as that. We just need to break things down. When I say break things down, you don't have to break things down physically. All I'm trying to tell you is split the topics. So if you have reflection of light, what are the topics, subtopics that you need to study under reflection of light? Can you divide these topics into furthermore topics as such? So it is simple as making a mind map. So if you get a snapshot of the entire chapter using this tool, it will be easier for you to understand and go through each and every topic and not skip anything as such, and also at the same time you won't be overwhelmed, right? So let's look at a sample mind map of reflection of light chapter. So in this chapter, as you can see, it can be split into 2 parts, that is reflection by plane surfaces, which you have been learning, I'm not sure, maybe if from grade 8 or grade 7, which you're already well aware of, and you can actually just brush through these topics. Reflection of light by plane mirror, nature of the image by formed by a plane mirror, what is a virtual image, how is it different from a real image, so on and so forth. But the second topic, that is the reflection by spherical surfaces, or when it comes to convex and concave mirror, you need to concentrate a little more on the different cases, as in when we keep the object in different positions in front of the concave mirror or convex mirror, it tends to form different kind of images depending upon the position of the object. Similarly, when we move on in detail into this topic, we need to understand a few terminologies of these spherical mirrors, like curvature, what is the center of curvature, what is the radius of curvature, and what is the principal focus, what is the principal axis, what do we mean by focal length, what is the relationship between image distance, object distance, and focal length, which is called as the mirror formula. I'm sure all of you are aware of it. Let's just quickly revise through all of these topics and try to solve few questions. So, when it comes to reflection of light, of course, the first thing that you would think of when you're preparing for the board examination, what do we mean by reflection? You will always concentrate on the definition. You can write the definition of a given topic or a given concept in multiple ways, but from the exam perspective, I would always suggest you to stick to the definition that is given in your textbook or given by your teacher, so that you don't miss out on the keywords, hence not losing marks, right? So what do we mean by reflection? Reflection of light, as you've studied in your previous classes as well, is nothing but bouncing back of light from any kind of surfaces. So when I say any kind of surfaces, it could be a polished mirror which gives you a perfectly nice looking image, and it could be a wall, it could be a paper, it could be you, it could be me. So all of us and all the objects around us actually reflect light. That is how we actually see each other or see anything around us. So why don't we see images as that which are formed in front of us? When we look at any of the objects, if they are reflecting light, that depends on the kind of reflection they perform. When a plain and polished surface is there, when a beam of light is incident on plain and polished surface, it basically sends back the same kind of parallel beam of light after reflection, hence makes a perfectly nice image. Whereas the other objects scatter the light all around them in all possible directions, hence they are only scattering the light rays that are falling onto them and not be able to form any kind of images as such, right? So what do we mean by reflection, or how do you write the definition of reflection? Reflection of light is bouncing back, or the process of sending back of light by any surface on which the light is falling onto. So as you can see here in the picture, of course we have considered only one ray of light in order to make our lives easier. Whenever you think of the light, it is not only one ray. I'm sure all of you know this. It is in the form of a beam. When I say beam, it is a collection of light rays. So as you have studied in your previous grades or lower grades, light is what? Light is a form of energy which always travels in straight line. It can travel through vacuum. It is an electromagnetic radiation, and it does not need a material medium to propagate. So here, whenever we are taking an example or a ray diagram, as we call it technically, to show how does an incident ray work, or how does the reflection ray work, all of these things we will be considering only one ray, which in order to make our lives easier. All right. So in this picture, as you can see, there we have considered only one ray of light, and it is falling onto the reflecting surface. Let's consider this as a mirror. When I shade it, this part of the surface is the non-reflecting surface, and the other one is the reflecting surface, right? So here what is happening is the ray which is getting falling, or which is actually falling onto the surface, is called as the incident ray, and we can denote it by capital I. And the ray which is getting sent back is obviously the reflected ray, and it can be denoted as capital R. What is this line then? This line is not a physical ray, and it is called as the normal. What do you mean by normal? Normal is just an imaginary line which is drawn perpendicular to the plane of the surface or reflecting surface at the point of incidence. So what do we mean by point of incidence? This is the point of incidence. Let me make it into other color so you can actually see this. So the purple dot that you see here is called as the point of incidence. Now what do we mean by point of incidence? Point of incidence is nothing but the point on the reflecting surface at which the incident ray comes and strikes it. So the normal is just an imaginary line that is drawn perpendicular to the reflecting surface at the point of incidence for a given incident ray. Now when I say normal drawn at the point of incidence, there could be multiple normals because there can be many incident rays as well. So for every point of incidence you can draw the normal as such. So if I draw a line here, that is, if I consider this as the incident ray and reflected ray will be in this fashion, right? So I can drop a perpendicular in this manner. Let me make it into other color so you can see it. So I call this as N dash, which is another normal drawn at the point of incidence, wherein here I dash is the another incident ray and R dash is another reflected ray. So normal can be drawn at any given point of incidence and always is an imaginary line. It is not a physical ray. Please remember that. Alright, with this basic knowledge of reflection, let's move on to laws of reflection. You have been studying laws of reflection for a very long time. I'm sure all of you know it by heart. But let's just brush through it very quickly. What is the first law of reflection? The law of reflection, first law of reflection states that the incident ray, the reflected ray and the normal drawn at the point of incidence all lie in the same plane. All these three things, that is the two rays, incident ray and the reflected ray and the normal drawn at the point of incidence, always lie in the same vertical plane. Okay? What does the second law state? Second law states that it is very simple. Angle of incidence is equal to the angle of reflection. I'm sure you would have by-hearted this and you all remember this very clearly. What is this angle of incidence and what is this angle of reflection? It is nothing but the incident ray. The angle made by the incident ray, let's call it angle I, and angle made by the reflected ray, let's call it angle R, with the normal is called as the angle of incidence and angle of reflection. These two things are always equal, no matter what kind of surface it is, no matter where the light is getting scattered or reflected, or if it is forming a perfect image or not, it doesn't matter. Laws of reflection are always true and followed by the light. If you are not able to see the image, it does not mean that the laws of reflection weren't followed. It doesn't matter what kind of reflecting surface it is, the laws of reflection always hold good. Okay? With this basic knowledge of reflection concept, let's look at the spherical mirrors. There are two kinds of spherical mirrors. One is the convex mirror, another is a concave mirror. So when we say convex mirror and a concave mirror, the basic example or the best easy example that I can give you right now is of a spoon. You go into your kitchen, pick up a spoon and tilt it either ways and check your image. How do you look when you look at the spoon? Of course, it has to be a little new spoon so that it is shiny and polished so you can see your image. Okay, the old spoons do not do that. So when you hold your spoon with the curvy surface, that is the KV surface, which is not bulged, the bulge surface outside, and look at the KV surface for your image, you see that yourself, the image of yourself is inverted. So such images are always real because it is a concave surface. The KV part of it is basically a concave surface and it is giving you a real and inverted image. What do we mean by real image? Real image is something which can be caught on screen. What is a virtual image? That is what you see in a plane mirror. Plane mirror produces a virtual and erect image. Virtual images are always erect in nature. Alright, so in the second surface, second kind of surface, which is bulgy outside, that is the convex surface. You look at yourself, you see that your image is erect, but it is quite small in size, that is diminished, right? So to give you more of a clear picture, why do we call it as a spherical mirrors, or how do they get their names, is by giving you this example or showing you this very simple demonstration. So as you can see there, imagine it as a normal ball here. Okay, I have a plastic ball, I cut a portion of it. Okay, you see this portion, I cut a portion of it and I silver this surface, this bulgy surface, so that I have this curve, this KV surface inside as a reflecting part. Now I have a concave mirror. Okay, similarly I take the same portion of the spherical or a spherical glass surface, or a, what do you call it, as a glass sphere, and I silver the inside KV portion of it, and then I will have the reflecting surface as the bulgy portion. Then it gives me a convex mirror. Okay, I have a concave mirror just to give you an idea here. So this is a concave mirror where you see the KV or the curved surface inside inner surface of this portion of the sphere is reflective in nature. The other part is not reflective in nature, it is silvered, right? So this is a concave mirror. So if I silver this part of the mirror, if I silver this part of the mirror, and if I make this part of the mirror, that is the outer portion, the bulgy surface of the mirror, as a reflecting surface, then I'll have a convex mirror. Okay, I hope you get an idea now. Now, when it comes to concave mirror and convex mirror, these two mirrors diverge the light and converge the light, but of course not both of them do both the functions. Concave mirror converges the light, while convex mirror diverges the light. So when I say diverges the light, I mean that it looks like it is coming from a particular point behind the mirror. This is done by the convex mirror. So as you can see here in the picture, this is a convex mirror. Okay, so when a parallel beam of light falls onto this surface, what is happening? It is getting reflected in such a fashion that when I extend these rays behind the mirror, they tend to meet at a single point on the principal axis. I'll come to what is principal axis in a while. On a certain axis which runs through the mirror, and this point is called as the focal point or principal focus of the spherical mirror, of the convex mirror first. So here, as you can see, the light looks like it is coming from a single point. So this becomes a diverging pattern of light. Hence, convex mirror is a diverging mirror, whereas concave mirror does all the converging. So as you can see it in the picture, whenever there is a beam of light, parallel beam of light that is hitting the mirror surface, concave mirror surface, all of these rays tend to meet at a single point on the horizontal line which is running through the mirror, and this is called as the principal axis, as I mentioned. Principal axis. So what do we mean by principal axis? Principal axis is a horizontal line that runs through the pole of the mirror. Let's look at these terminologies in detail. So when it comes to structure of the mirror, as you have already seen what is the structure and how do they get their name as spherical mirrors, because they are part of a sphere, right? So when a portion of a sphere is cut and silvered on one side, it becomes either a convex or a concave mirror depending upon the silvering side of it, right? So as a glass sphere, as we cut the portion of the mirror from a spherical surface or from a glass of sphere, there is definitely a center, there is definitely a radius, and hence there are certain terms that help us understand the structure of the concave and convex mirror better. So the first one is principal axis. What do we mean by principal axis? It is just a horizontal line that runs through the pole of the mirror. Now, what do we mean by the pole of the mirror? Pole of the mirror is nothing but the geometric center of the portion of the sphere that we have taken in, right? So as you can see here, we have denoted the pole as P. Pole is always denoted as capital P. The principal focus is denoted as capital F. You can just write it as focus. And what is this C? C is nothing but the center of curvature. As you have already seen in the previous picture, this here is a concave mirror and this here is a convex mirror. Both of them are a part of a sphere. So here there is a center of the sphere of which both the mirrors are a part, right? So this center of the sphere of which the mirror is a part is called as the center of curvature. What is it? The center of curvature. Similarly, there is a radius for this sphere, and this capital R, this radius is called as the radius of curvature. How do we define radius of curvature? Radius of curvature is nothing but the radius of the sphere of which the mirror is a part. Now that we have defined center of curvature and radius of curvature, let's look at what is principal focus. As you already seen in the picture, all of the light rays which are, in the case of concave mirror, the light rays tend to intersect or converge at a single point on the principal axis of the concave mirror. Hence, it is called as the principal focus. Similarly, when you look at the convex mirror, all the rays of light that are falling onto the convex mirror, which are getting reflected, appear to come from a single point behind the mirror on the principal axis. This is called as a principal focus. So the diverging light seems to come from the principal focus, and the converging light or the converging rays of light actually tend to converge at the principal focus in front of the concave mirror. So this is exactly the reason why it is called as the principal focus or focal point of spherical mirrors. With this understanding, let's look at a few important points or important methods in order to locate the images formed by spherical mirrors. In case of concave mirror, we have 6 cases or 6 different positions of objects that can be kept in front of the mirror, for which it forms different kind of images at different positions. In case of convex mirror, there are only 2 cases, which is pretty easy as such. Let's go ahead and look at these methods using which we can locate the images. So the first one, we call this method as the ray tracing. What do we call it as? We call this as ray tracing or rays of convenience. So when we have to select the rays for our convenience in order to locate the image, and hence the name here. So the first one, here we have just taken the example of a concave mirror. It is also true for the convex mirror. Absolutely holds good for the convex mirror as well. So when a ray of light which is parallel to the principal axis hits the surface of the concave mirror, it always passes through the principal focus. That's what you see here. So what is this point? It is point F, that is the principal focus of the concave mirror. And when there is a parallel ray of light, pardon my drawing skills here please. So when there is a parallel ray of light that is parallel to the principal axis, always passes through the principal focus after reflection. It is very important to remember and understand that this passing of this ray through the focus happens only after reflection if there is a ray that is incident parallelly to the principal axis. The next rule is just the inverse of it. What is the inverse of the first case? In first case, we had the ray which is parallel to the principal axis hitting the surface of the mirror. Here we have a ray which is incident passing through the principal focus. It will be parallel to the principal axis after reflection. So both of these cases are inverse to each other. The third one is a pretty easy one, and it is very easy to remember as well. Whenever there is a ray that is incident onto the mirror, or the surface of the mirror is passing through the center of curvature, it always traces back the same path, passing through the center of curvature again after reflection. So whenever we are trying to locate the image formed by a spherical surface, we always need to remember these three rays of convenience, and it will help us locate the needed image here. Okay, with these methods and basic knowledge of what are spherical mirrors and terminologies and all of these weapons, let's move ahead and understand the different positions at which the objects, when the objects are kept in front of the mirrors, where are these images formed. So these are the 6 cases for concave mirror where we keep the object very far away. Technically it is not infinity, it is just a far away distance when it is compared to the dimensions of the mirror as such. So please do not misunderstand saying that okay, infinite when we say at infinity, it cannot be measured or anything like that. Okay, it is just far away. So all of these 6 cases are as shown in the figures here. So these ray diagrams are really important. The arrow marks here are really important. Please understand it well and practice well when it comes to your examinations, because many of the questions are based on these ray diagrams, and you may have a direct question where you may be asked to draw the ray diagram for a given particular case, when the object is kept beyond C, when the object is kept at C, or when the object is kept between F and C, all of these things. Okay, let's look at 1 or 2 examples for each of these in these 6 cases and move on. So in the first case, when the object is kept far away, what kind of image is formed and where is it formed? So when it comes to image locating the image formed by a spherical surface or a spherical mirror as such, we need to keep 3 things in mind. First thing, position of the image, next is the nature of the image, and next is the size of the image. Where is it formed, what kind of image is formed, and what is the size of the image when it is compared to the object. Alright, so in the first case, when we keep an object which is very far away from the image, it obviously, the parallel beams of light come and hit the surface of the mirror, and as the first rule of ray tracing tells us, whenever there is a parallel ray of light or a ray that is parallel to the principal axis hits the surface of the mirror, it always passes through the principal focus. So we took one ray here and it passed through the principal focus here. Again, pardon my drawing skills. As you can see, it passed through the principal focus. This is one ray of convenience. Another one, we take the same kind of ray which is parallel to the principal axis, that is also passing through the principal focus. So as many rays as possible, if they are incident on the reflecting surface, that is a concave mirror here, even though there are billions and millions of parallel rays which are hitting the surface, they all converge at a single point, that is the principal focus. So what kind of image is formed? There is an image that is formed at the focus itself. What is the kind of the image or nature of the image? It is real and inverted. What is the position of the image? It is formed at F. And what is the size of the image? It is highly diminished and it is point sized. Alright, so when you look at the second case, that is when we keep the object at F itself. So in the first case we had kept it infinity, that is far away, and it formed the image at F. Now inversely what we are doing, we are keeping the object at F. So where is the image formed? It is formed at infinity. So these two cases are inverse of each other. So this is a nice way to remember all of these cases. Okay. So when it comes to third case, you see that we have kept the object a little closer to the mirror, wherein we have not kept it very close or in between C and F or anywhere as such. So we term this position as beyond C. It is not at very far away distance, so we cannot term this as at infinity. We will term this as beyond C. So when we keep the object beyond C, where is the image formed? The image is formed between F and C. It is a real and inverted image, and look at the size of the image. It is quite diminished when it is compared to the object. When you look at the fourth case, it is exactly the inverse of the third one. When we had kept the object beyond C, the image was formed between F and C. Now we are keeping the object between F and C, and the image is formed beyond C. And what kind of image is formed? As you can see here, it is a real, inverted, but quite enlarged in nature, right? Where is the position of the image? Image is formed beyond C. What is the nature of the image? It is real and inverted. What is the size of the image? It is quite enlarged in nature. Okay. Now, when we look at the fifth case, that is at C, it is the easiest of the cases I feel, and it's one of my favorites because it's easy to remember. It's as simple as that. Okay, so whenever we are keeping the object at C, what do we mean by C? It is the center of curvature. It forms a real and inverted image. Where does it form? It is exactly at the same position, but it is just inverted in nature. And what is the size of the image? It is exactly the same size as that of the object. Of all the 6 cases, the sixth one, that is whenever the object is kept between pole and the focus, that is whenever the object is kept very close to the mirror surface, only then a concave mirror gives you a virtual, erect and a very enlarged image. This is quite a good application when it comes to makeup mirrors or shaving mirrors. Hence, concave mirrors are usually used as makeup or shaving mirrors, or if it is also used by the dentists. If you have noticed, if you go to a dentist, they use a small tiny mirror in order to look at your teeth as such, correct? So that is a concave mirror, because when you hold the object very close to a concave mirror, it always gives you a virtual, erect and a very enlarged image. Alright, so these are the 6 cases, and you need to practice these ray diagrams as much as possible. I cannot stress enough on the significance of the ray diagrams when it comes to spherical surfaces or these mirrors. Okay, so this is just a snapshot of, or a summary of, all the 6 cases. As you can see, when we keep the object at infinity, the image is formed at focus. When we keep object at F, the image is formed at infinity. Similarly, when we keep object, let me color code it so that you understand. Okay, so when we keep the object beyond C, where is the image formed? Image is formed at, or image is formed between F and C. Inverse of it, when we keep the object between F and C, where is the image formed? Image is formed beyond C. So this is a good method to remember the ray diagrams, and also to remember where is the image formed in position and different aspects of these 6 cases for concave mirror. Moving on, let's look at a few applications of concave mirror. One of the applications, as I told you for the last case, that is when it forms a virtual, erect and a very enlarged image when the object is kept very close, that is between F and P. You get an application such as a shaving mirror, or a dentist's tool that they use, or a makeup mirror as well. But here in this case, you see that there is a aluminium rod or an conducting rod that is kept at the focus of this concave mirror, and it is used as a solar cooker. Now, how does this work? Since it's a concave mirror, it converges all of the solar energy, in this case, or sun rays, at one single point, and since it is focused at this point, it basically supplies enough amount of heat to heat up the pan and cook the food. Hence, it is used in solar cookers. It's a fun application. Moving on, as I already mentioned, the concave mirror is used as a shaving mirror, or it can be used as a makeup mirror for girls, right? And also it is used in torch lights and headlights of your vehicles. Now, how do they do this? In torch lights, I mean, you must have noticed when you switch on the torch, you get a very long beam of light, and also you see that the circle that is formed by the light rays is quite large in nature when it is compared to the torch. That's because there is a concave mirror that is fit into the torch light, and the bulb that is used to illuminate it is kept at the focus of the concave mirror, so that you get a very enlarged real and inverted image at quite a far distance from it. That is your second case. When we keep the object at focus, it forms a real and inverted image which is at a very far away distance, and the image is highly enlarged. So this concept, or this particular principle of concave mirror, is made use of in your torch lights, and also in the headlights of the headlights, as we commonly call it as the fog lights, where you need long beams of light in order for better visibility in your vehicles as such. Okay, it is the same case with the dish antenna as well. Now, when it comes to convex mirrors, once you have learned your concave mirror cases, now it must be a cakewalk for you to understand the convex mirror cases. There are only two cases in convex mirrors. When we keep the object quite far away from the mirror, it only forms an image which is virtual, erect, and very diminished. That is point-sized image at focus. Where is the position of the image in the first case? It is formed at focus. What is the nature of the image? It is virtual and direct. As I've already mentioned, convex mirrors cannot form any kind of real images at all. Okay? And what is the size of the image when it is compared to the object? It is point-sized or highly diminished. It is formed at the focus. When we bring in the object a little closer to the mirror, that is not very infinitely far away or not very far away from the mirror, then it forms a highly diminished erect and virtual image right before F, that is between F and P. These are the only two cases that you have to worry about when it comes to convex mirrors. Nothing else is possible here, like we have different cases in concave mirror at all. Okay, but convex mirror has its own wide range of applications when it comes to our daily life. So this one, I'm sure all of you would have seen and watched this particular clip or particular scene from the very famous movie called as Jurassic Park, right? So what is the statement that is written on the mirror? It says that objects are closer than they actually appear. What does it mean? It means that it is a convex mirror which is used, and it always gives you a diminished image, virtual, erect, and a diminished image, which often is a delusion that we get. Okay, the objects are quite far away. You might have noticed this in your vehicles, in your scooters, and many places as such. So why is this used as a rear view mirror? Because it gives a very wide range of view. Even though it gives us a very diminished image, it is still a virtual and erect image. Hence, it helps us basically while driving and while crossing, while cycling, or any vehicles that we use of. Okay. This is exactly the same reason it is also used in different shopping malls, or near the corners of the road. We have if we have a pin curve where the person who is coming from one side is not able to see what is coming from the other point, there they are used as the safety mirrors. It is exactly the same reason why they are used as the rear view mirrors as well, because they provide virtual, erect, diminished images, but they give us a very wide range of view. All right. Now that we have understood the uses and applications and different aspects for these two concave and convex mirrors, let's understand a simple relationship between a few aspects of these two mirrors. That is the mirror formula. Now, what is mirror formula? It is very simple. It is just a relationship between the image distance V, the object distance U, and the focal length F. What is focal length? Focal length is nothing but the distance between the pole of the mirror and the principal focus of the mirror. It is true for both convex and concave mirrors. There is also a relationship between the radius of curvature of the mirror and the focal length. As you can see here, radius of curvature is exactly double the focal length. So what can we write it as? We can write it as R is equal to 2F, or F is equal to R by 2. This is an equation which comes in very handy, as in very important when it comes to your examination perspective. You can get it as a 2-marker question, you can get it as a 1-marker question or an MCQ, wherein you will be given the radius of curvature and asked to calculate the focal length, or you would be given the focal length and you would be asked to calculate the radius of curvature. Either ways. Okay, so what do you mean by mirror formula? Mirror formula is a simple relationship between the image distance V. What is V here? Image distance. And what is U? U is the object distance. And what is F? F is the focal length of the mirror. Okay, what is focal length? Focal length is the distance between the pole of the mirror and the focus of the mirror, that is principal focus. Okay, so the final topic that is quite important when it comes to spherical mirrors is the sign conventions. So sign conventions are very, very important in order to solve a spherical mirror problem. Okay, you will see why when we solve a problem. Now, what are these sign conventions and why do we need it? We need it for the sake, in order to locate the image, in order to understand the kind of image that is formed by a spherical mirror, all of these aspects. Now, let's take the example of a concave mirror and let's understand what are the sign conventions. When I say sign conventions, these are kind of rules that you have to remember and assign plus or minus sign, that is positive or a negative sign to image distance, to object distance, to focal length, and many other different aspects of these two mirrors. Okay, so let's take the example of a concave mirror and understand this. So what is this first rule of sign convention? First rule of sign convention is that all the distances are measured from the pole of the mirror. When I say from the pole of the mirror, say for example, I have an object here. You see that AB is an object and it is at certain distance, say 10 centimeters, and it is denoted by U. So when I have to measure the object distance, all the distance, be it object distance or be it image distance, be it focal length, everything has to start from the pole. Let's mark the focus and let's mark the center of curvature for this mirror. Again, it is just a rough estimate of focus and the center of curvature for this mirror. So I have to start from the pole. So I have to begin from this pole and go in this direction so that I measure the object distance. If there is a real and inverted image that is formed somewhere here, so what is the image distance that I have to measure? That is V, has to be measured starting from the pole and in this direction. Okay. So when it comes to the incident rays that are falling onto the mirror surface, obviously it is coming from an object, because there are light rays that is falling onto the object, and this object is reflecting all of these light rays onto the mirror surface. So if I draw an incident ray like this, and the direction of the incident ray is obviously from my left to right. The second rule of sign convention is that all the distances which are measured in the direction of the incident ray, that is in this manner, that is left to right, have to be taken as positive. Now, if you remember, I said all the distances, first rule is that all the distances have to be measured from pole, correct? We did not have to assign any kind of signs, according to the first rule. So if I have to measure all the distances from the pole, and if I have to measure the object distance, I'll have to obviously start from the pole, and I have to go, let me just write this, incident ray, or it will be better termed as direction of the incident ray. So if the direction of the incident ray is in this direction, that is from my left to right, I'll have to start measuring the distances. All the distances are measured from the pole, that is in the opposite direction to this incident ray direction. So what did I first say? All the distances which are in the direction of the incident ray have to be taken positive. But when I have to measure the object distance, I'll have to start from the pole to the object. Hence, the object distance for any kind of mirror, be it convex or concave mirror, all of them have to be taken negative. Now, another thing is, whenever there is a real image formed, the real image is always in front of the mirror. So it is on the same side as that of the object. Hence, V is also negative, because we will be measuring in the direction opposite to the incident ray. Right? In case of the focal length of the concave mirror, it has to be measured again opposite to the direction of the incident ray, and hence in case of concave mirror, F is also negative. So for this, object distance is negative for both convex and concave mirror, no matter what kind of mirror it is. Image distance is negative when the image is real. Focal length is negative when it is a concave mirror. When it comes to convex mirror, the focal length is actually behind the mirror, and the incident ray is in this direction. So we'll have to start measuring it from the pole of the mirror, which is in the direction of the incident ray. Hence, the focal length of the mirror, that is for convex mirror, is always positive. The image distance for a convex mirror, that is image distance for a virtual images, are always positive. Virtual image distances, are always positive. Okay, and the last thing is that the height of the object, anything above the principal axis is positive, anything below the principal axis is negative. So if it's a negative image size or image height, then you need to understand the fact that it is a real image, real and inverted image. Alright, you will understand the sign conventions better when we solve one or two problems. With this understanding, let's move on to the last bit of this particular topic, that is the magnification of a given mirror. What is this magnification? You see that in different cases, when we kept the object in different positions in front of these mirrors, it formed different sized images. So magnification is nothing but the size of the image when it is compared to the size of the object. So how do we define it? It is defined as the ratio of the distance of the image to the distance of the object, or it can also be defined as the ratio of the height or size of the image to the height of the object. We can always have this formula handy when it comes to the problem solving or numericals of spherical images. Now, with all of this understanding, let's try and solve few questions or practice questions and one or two numerical problems. Okay, so first one is focal length of plane mirror is what? Options are infinity, 0, negative, none of these. First thing that comes into our mind is how can plane mirror have a focal length, right? Plane mirror is nothing but, you can imagine the plane mirror as a portion or as a part of a glass sphere or a reflecting sphere which is infinitely large. Okay, in that case, what happens to the focal length of the plane mirror or the radius of curvature of the plane mirror? It would be infinity, and half of the infinity obviously will be infinity again. So your answer will be A. Next, image formed by a plane mirror is what kind? Is it real and direct? Is it real and inverted? Is it virtual and direct, or virtual and inverted? So obviously all of you have learned this. The plane mirror always forms an image which is virtual and erect. So your answer will be C. Moving on. Write the relationship between U, V and F for mirrors. What is U? U is the object distance, V is the image distance, and F is the focal length of the mirror. So as we have already seen it, it's a very simple relationship. That is your mirror formula. What does mirror formula tell you? Mirror formula is the relationship between the image distance V plus the object distance U, that is equal to the reciprocal of the focal length F of the given spherical mirror. So you have 1 mark in your pocket again. So if the image formed by a plane mirror for all positions of the object placed in front of it is always diminished, erect and virtual, state the type of the image, state the type of the mirror. So as we have already seen in case of concave and convex mirrors, there's only one mirror which gives you a virtual erect images in all the positions where the object is kept. That is convex mirror. So your answer will be convex mirror. This is a 1 mark question. Again, you may be asked the same sort of question for any cases of concave mirror also. So it is important to know, if we keep the object in certain position, where will be the image formed, what kind of image will be formed, and so on and so forth. Moving on, name the type of mirrors used in headlights and in buses and cars. So as we have already discussed, what kind of mirror is used in headlights or fog lights? It is concave mirrors. So you have 1 more mark in your pocket. Moving on, we have an interesting question. That is, we'll have to locate and find the nature and size of the image in this particular described case. So an object of height 6 centimeters is placed at 15 centimeters from a concave mirror of focal length 10 centimeters. Now let's write down what are the things they have given us. Okay, it is very important to write down what the data that has been given to you. So first thing is focal length of the mirror, it is 10 centimeters, and height of the object, it is 6 centimeters. Where is it placed? It is placed at a distance of 15 centimeters. U is equal to 15 centimeters. So as per the sign conventions, the object distance is always negative, focal length is always negative for concave mirror, and height of the object is always positive because it is above the principal axis. Now let's try and draw the ray diagram. As you can see here, the distance of the object is greater than the focal length. Hence, it should be between C and F of the given mirror. So let's place an object here which is of 6 centimeters height. Let's give it A and B. This is C, this is F. Let's take one ray of convenience which is parallel to the principal axis, and we now know that when the object is placed between F and C, where will be the position of the image formed? It is always formed beyond C. So one ray that is parallel to the principal axis, it always passes through the principal focus, and another ray which is passing through the principal focus, it is always parallel to the principal axis after reflection, and you get an intersecting point of these two rays, drop a perpendicular from the principal axis, and you have a real and inverted image. Name it as B and A. You see that the nature of the image is perfectly right. The size of the image is quite enlarged, and hence you can validate your answer. Now, in order to calculate the image distance, let's use the mirror formula. What is mirror formula? It is 1 by U plus 1 by V is equal to 1 by F. What is V here? We do not know. That is what we are supposed to find out. What is U here? It is minus 1 by minus 15, because as you have seen it here, it is 15 centimeters as the object distance, and F is nothing but negative 10. So when we calculate this, 1 by V will be is equal to 1 by negative 10 plus 1 by 50. So we take the LCM, and LCM will be 30, and here we'll have minus 3, and here we'll have plus 2 and 1 by V. Please always remember, the answer that you get here is always the reciprocal of the value that you intend to actually calculate. That is your image distance. So your image distance will be negative 30 centimeters. So you can write the last sentence saying that image distance is negative 30 centimeters. This is also a validation that it is formed on the same side as that of the mirror. Now, we found out what is the position of the image, what is the distance of the image that is formed, and we can also calculate the size of the image using the magnification formula, right? So using all of these techniques, we have understood and we revised all of the concepts of reflection of light. And let's quickly summarize what are the topics that we learned. We learned what do we mean by reflection, we learned what is the reflection by spherical surfaces, and also we solved a few practice questions. I hope it was useful, and let's meet up in our next session. Till then, thank you.